Hello friends, I welcome you to lecture on variational problems with moving boundaries. First we will discuss some examples where we will see that one endpoint is fixed and the other point moves on a curve, and then we will take up a case where the one point is fixed and the other point moves on another curve. So let us see, we start with the example on the find the shortest distance between the point P1 that is 1 0 and the ellipse which is given by 4x square plus 9y square equal to 36. We know that the arc length P1 P2 of the curve y equal to yx is given by I yx equal to integral x1 to x2 under root 1 plus by dash square dx. Now here x1 by 1 is the point 1 0, so we will write 1 for x1 and therefore we have integral over x1 to x2 under root 1 plus by dash square dx, where x2 y2 will lie on the ellipse 4x square plus 9y square equal to 36. Now here the functional is integral 1 to x2 under root 1 plus by dash square dx. So if you compare it with the standard form of the functional, we can see that fx by y dash is under root 1 plus by dash square, and so ax by here is equal to 1. Now from Euler's equation, which we write as delta f over delta y minus d over dx delta f over delta y dash equal to 0, we see that the Euler's equation reduces to minus d over dx by dash over 1 plus by dash square equal to 0, because here fx by y dash is not depending on y, so its partial derivative with respect to y will be 0, and when we differentiate this with respect to y dash, we will get by dash over under root 1 plus by dash square. So Euler's equation reduces to minus d over dx of by dash over 1 plus by dash square equal to 0, and we have seen in our previous lecture that when we solve this equation, what we get is y equal to c1x plus c2, so which is the equation of a straight line. Now since this line passes through the point 1 0 which is x1 y1, we will have c2 equal to minus c1, and since the point x2 y2 lies on 4x square plus 9y square equal to 36, we have 4x2 square plus 9y2 square equal to 36. Now if you solve 4x square plus 9y square equal to 36, you can write it as a function, y as a function of x, and y will be equal to 2 by 3 under root 9 minus x square. Now here we see that we have this situation. This is ellipse 4x square plus 9y square equal to 36. So this is 3 0, here we have minus 3 0, and this is 0 2, this is 0 minus 2. Minus 2, and here is the point, let us say 1 0, and x2 y2 is say point here. So shortest distance occurs along a straight line y equal to c1x plus c2x, and 4x square plus 9y square, so we write as y equal to 36 is minus 4x square, y is equal to 36 minus 4x square divided by under root divided by 1 by 3, so plus minus, okay, and this I can write as plus minus 2 by 3 under root 9 minus x square. Now we are taking here y equal to positive, okay, we are taking y here, y equal to 2 by 3 under root 9 minus x square. one can take y equal to minus under root minus 2 by 3 under root 9 minus x square. Then the other point which is symmetric corresponding to x2 by 2 here below this x-axis will also be can be also be taken as x2 by 2. So we are taking y equal to 2 by 3 under root 9 minus x square and we are calling it as phi x. Now from the transversality condition, because x2 by 2 lies on the curve that is the ellipse, it will satisfy the transversality condition f plus phi dash minus y dash into f y dash at x equal to x2 equal to 0. Now here f is equal to 1 plus y dash square raised to the power half, and phi dash, this is y equal to phi x. So when you differentiate, what you get is phi dash x equal to 2 by 3 1 by 2 under root 9 minus x square into minus 2x. So this will give you minus 2x upon 3 under root 9 minus x square. So phi dash is minus 2x upon 3 under root 9 minus x square minus y dash and then multiplied by f y dash. F y dash is y dash divided by under root 1 plus y dash square, evaluated at x equal to x2 equal to 0. And when we simplify this equation, what we get is 3 times 9 minus x2 square raised to the power half is equal to 2x2 into c1. And what we have is y equal to c1x plus c2. Okay, so y2 equal to, this implies y2 equal to c1x2 plus c2. Now the y equal to c1x plus c2, it passes through y equal to c1x plus c2 passes through 1 0, so we get zero equal to c1 plus c2, which implies that c2 is equal to minus c1. So put here c2 equal to minus c1, so we get c1 times x2 minus 1. So we get y2 equal to c1 into x2 minus 1, and therefore 4x2 plus 9 by 2 square equal to 36 reduces to 4x2 square plus 9c1 square into x2 minus 1 whole square equal to 36. Now the question 4, if you look at the question 4, the question 4 on squaring both sides gives you 9 times 9 minus x2 square equal to 4x2 square into c1 square, and equation 5 is 4 times 9 minus x2 square is equal to 9c1 square into x2 minus 1 whole square. So if you divide the equation, divide these two equations and simplify, you get x2 equal to 9 by 5. We are taking positive value of x2 here. If you take negative value of x2, the corresponding value of that by 2 that you get will not give you the shortest distance. So we are taking x2 equal to 9 by 5. Now from 4, 3 times 9 minus x2 square raised to the power half equal to 2x2 c1, what we get is, on putting the value of x2 as 9 by 5, we get c1 equal to 2, and since c2 is minus c1, we get c2 equal to minus c2, c2 equal to minus 2. So since y2 equal to c1 times x2 minus 1, we can put the value of c1 as 2 and x2 as 9 by 5 to arrive at the value of y2, which is 8 by 5. Thus we can say that the shortest distance is attained along the line y equal to c1x plus c2, which is c1 is 2, so 2x minus 2 or 2 times x minus 1. So the shortest distance is attained along the line y equal to 2 times x minus 1, and the required shortest distance is the point x2 y2 is coming out to be 9 by 5, 8 by 5, So this is shortest distance is under root 9 by 5 minus 1 whole square, 8 by 5 minus 0 whole square. So which is equal to 4 square root 5 divided by 5. So this is example 1 where we have calculated the shortest distance between a fixed point and the other point which x2 I2 which varies along the curve, which is an ellipse. Now let us take another problem where we are going to find out the shortest distance between the parabola by square equal to 4x and the circle x minus 9 whole square plus by square equal to 4. So here both the points x1 by 1 and x2 by 2 will be moving such that the distance between the 2 points is distance between the 2 curves is the shortest distance. So let us draw the figure first. So we have to find the shortest distance between the parabola by square equal to 4x and the circle. So parabola here is by square equal to 4x and circle is x minus 9 whole square plus by square equal to 4. So let us draw the figure. Let us say this is your parabola by square equal to 4x. The circle has center at 90. Circle has center at 90 and radius 2. So let us say this is your circle and radius is 2. So this is your circle, x minus 9 whole square plus by square equal to 4. We have, let us say x1 by 1 is point here on the circle and x2 by 2 is a point here on the parabola, and we are finding the shortest distance between the 2 points, between the 2 curves. So we have to find the shortest distance between the point x1 by 1 which lies on the circle, x minus 9 whole square plus y square equal to 4, and x2 by 2 which lies on the parabola y square equal to 4x. Now the equation of the circle can be put as y equal to 4 minus x minus 9 whole square raised to the power half. We are taking positive value of y here, and similarly y square equal to 4x, which we are writing as y equal to 2 root x. We are finding the shortest distance in the positive quadrant. So let us say y equal to under root 4 minus x minus 9 whole square under root, we are under root 4 minus x minus 9 whole square we write as phi x, and y equal to 2 root x we write as psi x. Then the arc length P1 P2 of the extremizing curve, this is the extremizing curve. So the arc length P1 P2 of the extremizing curve will be given by integral x1 to x2 under root 1 plus y dash square under root 1 plus y dash square dx. Here we note that both the endpoints x1 by 1 and x2 by 2 are moving. x1 by 1 is moving on the circle while x2 by 2 is moving on the parabola. Now here again fx by y dash is under root 1 plus y dash square, and therefore from the Euler's theorem we get that y is equal to c1x plus c2. Now since p1 and p2 lie on 3, p1 and p2 lie on the 3, which is the equation of a straight line, we get y1 equal to c1x1 plus c2 and y2 equal to c1x2 plus c2. And moreover p1 and p2 lie on the circle and parabola respectively. So x1 by 1 lies on circle, therefore y1 equal to 4 minus x1 minus 9 whole square raised to the power half, and x2 by 2 lies on parabola, so y2 is equal to 2 square root x2. Now from the equations 4 and 5 we have c1 x1 plus c2 equal to y1 is equal to 4 minus x1 minus 9 whole square raised to the power half, and similarly c1 x2 plus c2, which is y2, is equal to 2 root x2. Now since P1 and P2 are both moving, we will have to use the transversality conditions at P1 and P2 for the curve y equal to phi x and for the curve y equal to psi x. At the transversality condition at the point P1 will be f plus phi dash minus bi dash into f y dash at x equal to x1 equal to 0, and the transversality condition at the point P2 will be f plus psi dash minus bi dash into f y dash at x equal to x2 equal to 0. Now f is under root 1 plus bi dash square, so 1 plus bi dash square to the power half plus, and phi dash, phi is equal to, phi x is equal to we are writing phi x equal to 4 minus phi x equal to 4 minus x minus 9 whole square under root. So when you find phi dash x here, what you get is 1 by 2 times under root 4 minus x minus 9 whole square into minus 2 times x minus 9. So this 2 will cancel and we get minus x minus 9 divided by under root 4 minus x minus 9 whole square. So let us put the value of phi dash as minus x minus 9 over 4 minus x minus 9 whole square root, and then minus bi dash into f y dash. F y dash is the partial derivative of f x y dash, which is under root 1 plus bi dash square with respect to y dash. So it is bi dash over 1 plus bi dash square to the power half. It is at x equal to x1 is equal to 0, and similarly let us write the transversality condition at the point P2. So we have f equal to 1 plus bi dash square to the power half divide plus 1 by psi dash is psi x is equal to by this curve. This curve we are writing y equal to 2 root x is equal to psi x. So psi dash x equal to 1 by root x. So let us put the value of psi dash as 1 by root x minus bi dash multiplied by bi dash over under root 1 plus bi dash square at the point x equal to x2 is equal to 0. Now y is equal to c1x plus c2, and therefore if you differentiate y with respect to x, you get bi dash equal to c1. So let us put c1 bi dash equal to c1 in equation 8, and then the equation 8 becomes 1 plus c1 square to the power half plus inside the curly bracket we have minus x1 minus 9 over 4 minus x1 minus 9 whole square to the power half minus c1 into c1 upon 1 plus c1 square to the power half equal to 0. On simplifying, this gives you c1 times x1 minus 9 equal to 4 minus x1 minus 9 whole square to the power half. Similarly, if you put bi dash equal to c1 in equation 9 and then simplify, what you get is c1 equal to minus root x2, and from the equation 6 and 10 let us look at the equation 6. Equation 6 is c1 x1 plus c2, c1 x1 plus c2 equal to 4 minus x1 minus 9 whole square under root, this is 6, and what is 10? 10 is c1 times x1 minus 9. So this is equal to c1 times x1 minus 9. So c1 times x1 minus 9 equal to 4 minus x1 minus 9 whole square to the power half. So what we will get, c1 x1 will cancel and we will get c1 x1 will cancel, we will get c2 equal to minus 9 c1. So we get c2 equal to minus 9 c1, and from 11 and 12, let us look at 11 and 12. 11th equation is c1 equal to minus root x2, 12th equation is c2 equal to minus 9 c1, so c2 is equal to 9 root x2 we get, and putting the values of c1 and c2 in equation 7. So we have got the value of c1 as minus root x2 and c2 as 9 root x2. Let us put them in equation 7. 7 is this one, c1 x2 plus C2 equal to 2 rated x2. We would put the values of C1, C2 in terms of x2 and simplify this equation. We will get the value of x2 as 7, and hence from 5 we get by 2 equal to 2 root x2. So we get by 2 equal to 2 root 7, and thus the coordinates of the point P2 are P2, this is P2, this is P2 point. So it is root 7 2 root 7. So x2 by 2 point is x2 by 2 point is 7 root 2 root 7, and since x2 is equal to 7, C1 is equal to C1 was equal to minus root x2, so we get minus root 7. So C1 is minus root 7 and C2 is 9 root 7. C2 is 9 root 7. So now let us simplify this equation. C1 times x1 minus 9, C1 times x1 minus 9 equal to 4 minus x1 minus 9 whole square to the power half. We get x1 equal to 9 plus minus 1 by root 2. So 9 x1 here, x1 comes out to be 9 plus minus 1 by root 2. Okay, so 9 plus minus 1 by root 2 and the corresponding value of by comes out to be plus minus root 7 by 2, and so the required extremal is by equal to C1x plus C2, that is minus x root 7 plus 9 root 7, and the required SD is, so here we will see that x1 is equal to x1 is equal to this is 7, and then here we have 9 minus root 1 by root 2. Okay, so so x2 by 2 was equal to 7 and 2 root 7, and here we have x1 equal to 9 plus minus 1 by root 2, and we have by 1 equal to plus minus root 7 by 2. So here we get SD as integral 7 to minus 9 minus 1 by root 2 1 plus by dash square is 1 plus C1 square to the power half, and this is shortest distance is equal to integral under x1 to x2 under root 1 plus by dash square dx. By dash is equal to C1, so integral x1 to x2 under root 1 plus C1 square dx, and C1 is equal to root minus root 7. So this is x1 to x2 under root 1 plus minus root 7 whole square dx. So 7 plus 1 means 8. So root 8, that means 2 root 2, and then x1 minus x2 dx. And x1 minus x2 means we are getting x2 equal to 7. So this will be equal to 2 root 2, x2 is equal to 7 minus x1 is equal to 9 minus 1 by root 2 we are getting. This will be coming out to be negative, so that is why we are writing 9 minus 1 by root 2. If we write, okay, so 2 root 2, 7 minus x1 by 1 to x2 by 2. Okay, so this will be 9 minus 1 by root 2 minus here we are seeing that we have to take x2 equal to, we have to take x1 as 9 minus this upper limit we have to take as 9 minus 1 by root 2, lower limit will have to be taken as 7, because this is how much? This is 2 root 2 into 2 minus 1 by root 2. So that means we have to take the modulus here, because it turns out that the if we take x1 as 7 and x2 as 9 minus 1 by root 2, then okay, x1 9 minus 1 by root 2 minus, yes. So here x1, actually x1 is 9 minus 1 by root 2 and x2 is 7. So x2 minus x1 comes out to be negative, so we will have to, because the distance is always positive, so we have to take 9 minus 1 by root 2 minus 7, and this will give you 2 root 2 into 2 minus 1 by 8, or you can say root 8 into 2 minus. This is because x2 is 7 and x1 is 9 minus 1 by root 2. So 7 minus 9 minus 1 by root 2 comes out to be negative. So we have to consider, and distance is always positive, so we have to consider 9 minus 1 by root 2 minus 7. So that will give us the shortest distance. Now we will consider the one-sided variation. Let us consider the functional I by x equal to integral x1 to x2 fx by y dash dx, and let us assume that a restriction is imposed on the class of permissible curves in such a way that the curves cannot pass through points of a certain region are bounded by the curve psi x by equal to 0. So let us see, we have this situation. Let us say we have this situation. We have a region R, we have a point A here and another point B here. This curve R, this region R is bounded by the curve psi x by equal to 0. So the region R is bounded by the curve psi x y equal to 0, and we want that function, that extremal on which the restriction is imposed that it cannot pass through the points of the region R. So what we will have in such a problem, one of the following two situations may arise. First situation is when the extremizing curve C passes through a region which is completely outside R. For example, like this. So this curve C completely lies outside the region R. Okay, so when the extremizing curve C passes through a region which is completely outside R, in this case the presence of the privated region R, the privated region is R, does not at all affect the properties of the functional and its variation in the neighborhood of C, and so the extremizing curve must be an extremal. Now let us say this situation 2. In the second situation, the extremizing curve C consists of arcs lying outside the boundary of R and also consists of parts of the boundary of the region R. So we may have a situation like this. So we may have a situation like this where the extremizing curve C consists of arcs which lie outside the boundary of the region R, that is AM, and then AM and QB, and the also consists of parts of the boundary of the region R, that is MN and P and PQ. In this situation, only one-sided variations of the curve are possible on parts of the boundary of the region R. Because this region is privated, okay, so only one-sided variations are possible on the parts of the boundary of the region R. Now since the permissible curves are privated from entering R, parts of the curve C that lie outside the boundary of R must therefore be extremals. The AM, the parts of the curve that lie outside the boundary, so that is AM and QB, they must therefore be extremals, and Since on these parts two-sided variations are possible, and therefore in order to construct the required optimizing curve, we must derive conditions at the points of transition M and P and Q. In what follows, we shall derive the condition at the point M. In exactly analogous manner, the necessary conditions at the other points N, P and Q can be derived. While computing the variation delta I of the functional I equal to x1 to x2 fx by y dash dx, we assume that the variation is caused solely by the displacement of the point M. The point M is having coordinates x bar, y bar. So, by the displacement of the point M, x bar, y bar on the curve psi x y equal to 0, that is for any position of the point M on the curve, AM is an extremal and the segment MN PQB, MN PQB, MN PQB MN PQB does not vary. So, in the functional I1 that is x1 to x bar fx by y dash dx, I1 the upper boundary point x bar moves along the boundary of the region R, and so y is equal to phi x is the equation of the boundary as deduced from psi x y equal to 0. So, psi x y equal to 0 we are writing as y equal to phi x. So, x bar y bar point moves on the boundary of the region R, and so y equal to phi x of which is the equation of the boundary gives you y bar equal to phi x bar. Now, then it follows that delta I1 equal to f plus phi dash minus y dash f y dash at x equal to x bar into delta x bar, which is which follows in, from the article on variational problem with moving boundaries. So, delta I1 is this, and the functional I2 equal to x bar to x2 fx by y dash dx also has a moving boundary point, which is your x bar y bar. So, but in the neighborhood of the point x bar by bar, the curve y equal to phi x on which an extremum can be achieved does not vary, and so it follows that the variation of the functional I2 in the transition of the point M x bar y bar to the position M dash x bar plus delta x. So, let us say M dash is here, M dash is x bar plus delta x bar, y bar plus delta y bar. Only reduces to a change in the lower limit of integration, and we have delta I2 equal to x bar plus delta x bar to x2 fx by y dash dx minus x bar to x2 fx by y dash dx. This is the change in the functional in the value of I2 when the point x bar y bar moves to x bar plus delta x bar y bar plus delta y bar. So, this now this difference of the two integrals is nothing but minus x bar to x bar plus delta x bar fx by phi fx by y dash dx, but y is equal to phi x. So, it is fx phi x phi dash x dx. Since y equal to phi x lies by x since y equal to phi x is on the interval x bar to and x bar plus delta x bar. Okay. Now let us use the mean value theorem. So, by using mean value theorem, delta I2, which can be written as see delta I2 is minus x bar to x bar plus delta x bar f x phi x phi dash x dx. By mean value theorem we can write it as this is equal to minus f x phi dash at x bar plus theta delta x bar, where theta lies between 0 and 1 into delta x bar. So by mean value theorem we can write it as minus fx phi dash x bar plus theta x delta x bar into delta x bar, where theta lies in the open interval 0 1. Now by the continuity of fx phi dash, fx phi dash x bar plus theta delta x bar is equal to fx phi dash at x equal to x bar minus alpha, where alpha goes to 0 as delta x bar goes to 0, and therefore I2 delta I2 is equal to minus fx phi dash at x equal to x bar into delta x bar plus alpha delta x bar. Now which implies that delta I2, this delta I2, del I2 or delta I2, this is equal to minus fx phi dash into delta x bar. So this is delta I2, and from 3 and 4 we find delta I equal to, so let us see, yes, this 3 gives you delta I1 equal to f plus phi dash minus bi dash f bi dash at x equal to x bar delta x bar, and we have just now seen the equation 4, which is delta I2 equal to minus fx phi dash delta x. Let us put these values to get this delta I, the variation in I. So delta I is equal to delta I1 plus delta I2, and what we get is delta I equal to this quantity from by combining 3 and 4. So with by x bar equal to phi x bar. So since delta x bar is arbitrary, the necessary condition for an extremum delta I goes to 0 will then imply that fx by y dash minus fx phi dash minus bi dash minus phi dash into f by dash x by y dash at x equal to x bar equal to 0. Now let us apply the mean value theorem here in the first two terms, fx by y dash minus fx by phi dash. So by applying mean value theorem we will get this as bi dash minus phi dash into f by dash x by q, where q lies between bi dash x bar and phi dash x bar. Now let us apply the mean value theorem to fx by y dash minus fx phi dash, fx by y dash minus fx phi fx by phi dash. So by mean value theorem this will be equal to bi dash minus phi dash into fx by q, where q lies between bi dash x bar and phi dash x bar. So the first two terms here, fx by y dash minus fx by phi dash can be expressed as bi dash minus phi dash into f by dash x by q. So we can take bi dash minus phi dash common, and we have bi dash minus phi dash times f by dash x by q. This is f by dash f by dash x by q minus f by dash x by y dash at x equal to x bar is equal to 0. And applying the mean value theorem again, what we will have, let us see. So f by dash x by q minus f by dash x by y dash. Let us apply mean value theorem here again. So this will be q minus bi dash into f by dash f by dash f x by y dash q bar. So we will have this, so we have bi dash minus phi dash into q minus bi dash into f by dash x by q bar at x equal to x bar, where q bar lies between q and bi dash x bar. Now let us assume that f by dash x by q bar is not equal to 0, which holds true for many variational problems. Then we shall obtain by dash x bar equal to phi dash x bar, because if q equal to by dash x bar will hold only when by dash x bar equal to phi dash x bar, because q lies between by dash x bar and phi dash x bar. So q can be equal to by dash x bar only when by dash x bar is equal to phi dash x bar. But y dash x bar equal to phi dash x bar means what? By dash x bar is equal to phi dash x bar, means that at the point x bar by bar, the slope of the extremal, okay, slope of the extremal, which is by dash x bar, is equal to the slope of the curve y equal to phi x. So this means that the extremal meets the curve tangentially. So at the point M, which is x bar by bar, the extremal AM meets the boundary Mn tangentially. So this is what I have to say in this lecture. Thank you very much for your attention.